So last time we gave Lua its own memory allocation function, which is this thing here, this L_alloc, and all we did was we copied Lua's exact allocation function, and we got this little test program that just makes a new state, Lua state, and closes it. So this time I thought we'd have a go at writing our own little memory pool, or our own little Arena memory pool. So the idea behind that is what we're going to do is we're going to, rather than each memory allocation coming from this realloc and free, which are provided by the C runtime, we're going to allocate a big block of memory, or as big or as small as we want. So we're just going to allocate one block, and then we're going to have Lua get all its memory allocations from that one block. And that's what the arena means in Arena memory allocation. There's this one arena where all the allocations come from. And we're going to do that. We're going to allocate like chunks, little pieces out of this arena. And when we come to deallocate the memory or free it, we're actually not going to free it at all. We're just going to burn through all this memory. And at the end, when we finish our program, we just dump the whole arena. So one of the reasons you might do something like this is because it's quicker. Because not freeing memory is quicker than freeing memory. Because a lot of the time you'll find in memory allocation and deallocation, it's actually the deallocation can be quite time consuming. You got to work out, what do you do with this piece of memory? Who do you give it to? Do you try and coalesce it with another piece of memory to try and stop fragmentation? Do you give it back to the operating system? So there can be quite a lot of work that needs to be done there. But in Lua, I'm just going to prove the point here. We're going to write our own little Arena allocator, which may or may not be suitable for your needs. But the point here is that you can write your own memory pool or allocation system, and depending on how you're using Lua, this might be a really good thing, or it might not be, or it might not be worth your trouble. But usually you can get better performance, or you can allocate the memory in the way you want to, and that's fits in with what Lua's doing, which is it's an extensible library. It's not like it doesn't do this out of the box, but you can do it, and that's what's cool about it. So the way we do that is we've got our new state, and we've got our allocation function, which is just a static function. So it's a stateless allocator at this point. It doesn't need to know any other information apart from what we pass it in. But we did also pass in this user data thing, which is, again, not a Lua user data. It's just a C pointer to something that we can give to the allocation function every time we allocate. So what we're going to do there is we'll pass our memory pool in at that point. And what that means is the first allocation for the Lua state will get the memory pool. And every further allocation will also have that same memory pool. And to do that, we might as well just make an instance of this Lua mem that we created, this little struct that's got our static function in. Let's just make one of those, and we'll call it pool. That's our memory pool. And in this instance, we're actually going to put it on the stack. So this is and I say the stack, it's the C stack, the C++ stack, not the Lua stack. So that's another thing we can do now, is that we can actually make this script completely allocationless, because we're only going to allocate the memory on the stack. We're not going to do any heap allocations. So we can make it heapless, if you know what I mean. So it's quite cool that you can do this kind of stuff. So as the user data, I'll just pass in the address to the pool. So there you go. I've just made one of these Lua mems, which hasn't got really anything in it apart from this static function. And that gets passed through as the user data, which will come out here in this allocation function. So I can just cast it back to our Lua mem there, and I'll call it pool. So I know that every one of these is going to be a Lua mem, because I've told it so in our program. And if you wanted different allocators for different Lua states, then you'd need a different one of these functions. So that just basically that's passed our pool through to every single allocation. So that's a good start. We now have some states that we can use. We've got the state that we can put inside this struct. So how do we begin? Well, let's begin by redefining these free and realloc inside here as actual functions. So let's define this free function. which wants a pointer. So instead of calling free there, we'll call free on our pool. And we've also got a realloc function, which is, yeah, which returns the pointer to the new memory. So that returns a pointer. It takes a pointer and the new size of the object, and these are size t's. For now, I'll just call the original C functions that we were calling. And I'll pass that through to the pool. So that's already a reasonable start, is that we've swapped out our static function. We're using this now, we don't need that. We've swapped out our static function for one that passes through a memory pool and then just forwards to the memory pool. As you can see in our case, the memory pool actually is just the normal memory allocation. But the cool thing now is that we can change that just by changing that pool to a different one. Let's just see if that builds. It doesn't, because realloc recursive control. Oh, these doesn't like having these names the same. It can't distinguish them. So let's just call this reallocate. Let's give it a different name. And we'll call this one deallocate. And we'll swap those out there. That's a deallocate, and that is a reallocate. So it's not crashed. We don't know quite if it's working, but we're pretty sure reasonably sure that's just basically a refactor of what we've got. We haven't changed the way the program works, but we are using the memory pool that we've passed through to do the allocations. So to make this a bit better, or I say better, let's just make it different. What we really want to do is allocate from this block, and one of the ways to do that is we'll pass in the block of memory that we want this to allocate from. And one of the ways you do that is you pass it in the address of the start of the block and the address of the end of the block. So what we're saying is when you make me one of these pools, tell me this pool, because this arena is just this one block of memory. So just tell me what the one block of memory is that you've got, and tell it me as the begin and end pointers, and then I'll just store those in here. So now that's our arena basically, and then let's store those. Begin and end. So now we have our arena. We've got our block of memory. How do we allocate from that? We've got a reallocate and a deallocate. Let's just build a basic allocate, and that needs to just take the size that we want to allocate, the number of bytes that we want to allocate. So we just build a basic allocate in there. So what we'd have to do is, well, we need to know where are we up to in this block of memory, because remember, we're going to keep allocating little pieces out of this, and we're never going to deallocate. We're just going to burn through it. Every time we need a new piece of memory, we'll just get a new piece off the end. So we need to know where we're up to. So we need to know the current position inside this memory pool, and that will initialize right at the start to the begin part. So to allocate a new pointer, that will return a pointer. This allocation is going to return a pointer to a piece of memory. It will just be, well, the new pointer will just be wherever we are at the current, and then we'll just advance the current onwards by the size, and then we'll return the pointer. So that's our basic, really basic allocation, is that we're just going to take where we're up to in this pool and, give that to whoever needed the memory, and then move on by the amount of size they said it was going to work by. Doesn't look like that's going to compile. because it can't add that because current's unknown size. So we'll just change current to be a char because that's a 1 byte size. So when we add size on, it knows to add that many bytes on. And begin won't work then, so we'll need to cast that. So that's the same thing now, except we're just using a 1 byte type to index this thing. So we know that this size is in bytes. Just make that clearer there. Size in bytes. So there you go. So we advance on by the number of bytes, and then we return the pointer. Let's see if that works. Oh, now we need to construct this, and we need to pass in our memory pool. So it needs the memory it wants to operate on. So how do we get some memory? Well, one of the easy ways to do it is let's just make some here. So just make on the C stack, the C++ stack. We need let's say pool size is and let's allocate well, how much memory you can put on the stack might be dependent on your platform, but let's just allocate 20 kilobytes. So we're just going to put 20 kilobytes of memory on the stack, and we're going to use that to allocate all our Lua memory from. So this is great. Lua's not even going to go to the OS to get new memory. It's just going to get it from the stack that we've already allocated. We need to pass it in the begin, which is the first byte of that memory, and the end is going to be memory. It's going to be memory pool size. The last byte is that, I believe. So that's the last byte in that array, and we need the address of that. Is that right? So yeah, that's just passing in the begin and the end of this little array of characters that we've just put on the stack. So that's our memory pool. We've got 20 kilobytes of memory there, and we're going to pass that through to Lua to do its allocations from. So let's see if that works. So that's already working. We've got the pool there. We've got our allocation function, and let's get Lua to call. Let's get Lua to use that new allocation function. So if the size is 0, that's a free. So that's the deallocate. So we'll leave that as it is for now. Now our deallocation function actually is now going to be this. It's going to be nothing, because let's get rid of that. Don't want to complain. We are just burning through memory. So this is now our deallocation function. Nothing. It's a comment. We allocate the memory. We move on to the pointer to the next part, and when we deallocate, we never give the memory back. And that sounds like in most cases you'd be thinking, oh, that's a memory leak, but it's not, because at the end of this program, the arena gets freed. So that memory does get freed by the arena, but it's not going to get like deallocated in these little pieces. And if you wanted to, you could start deallocating there and do something with the memory. But in our case here, I'm going to say, well, we want some super speed, so we're just not going to deallocate at all. And let's just see. So deallocate, that works. And in Lua's case, it said if the new size is more than 0, so this is the new size of the block it wants, it's just calling reallocate, and it's based that on what the C reallocate did. But we can probably make that a bit clearer here. So what we're saying in this case is if the pointer, this is the pointer it passed in for possibly was the old memory address. If the pointer that you passed in for your old piece of memory was null, then this must be an allocation, because the old pointer is null and you're telling me you want something of a new size. So this is just a standard allocation at this point. So we just want to do that. So, and if the pointer isn't null, it must be a reallocation. So let's call the reallocate. So we've got allocate and we've got reallocate. So you can see there we've got deallocate, allocate, and reallocate. So this last one is where the pointer is not null and the size is different, or the size is more than 0. So we're definitely doing a reallocation there. So let's write our reallocation as well. And to do that, we will just, well, the first thing we're going to need is we'll do an allocation of the new size. So this is going to be our new piece of memory that we want to point to. And we can just call out allocate on that because we've already written that. And we want new size. So we've allocated some new memory. And to do a reallocation, we need to copy the old memory into the new place. And we can just do that with a mem copy. So it wants the destination, which is the new place that we've allocated. The source is the old pointer we passed in. And the size, and now here's the odd one. We've only got the new size. We don't have the old size. Now I think the C runtime was able to do this because it somehow stored the size of the old memory inside that allocation somewhere, but we haven't done that. So we really need the size of the old block that we're copying because we need to copy the old amount of size into the new block. So let's have ours pass in the old size. And that was one of the parameters in that Lua function. So we allocate a new block, we copy the size of the old block into the new block, and then we return the new block. Oh, and we also have to deallocate the old block, which is a pointer. Yeah. So we allocate a new block, copy the old memory in, deallocate, and of course our deallocate actually does nothing, but we're calling it here for completeness anyway, in case somebody wanted to fill this in with a new, with an actual deallocation scheme. But essentially, yeah, that's done pretty much what we wanted, I think. So the only thing we're going to have is probably get a compiler from that. Function does not take 2 arguments. So to reallocate now, we need the old size and the new size. So just to be clear, that's what these parameters were for this allocation function. It was the user data, which in our case now is our memory pool, the pointer to the old piece of memory that is possibly being reallocated or freed, and that's the O size is the original size of the block, and that would, you'd only get that if there's a pointer in there, and the new size is the size of the block that we want to allocate. So this does allocation and free depending on the parameters. But there you can see it's handling it all down there, and we've used original size now, so we don't need that anymore. So that's our new allocation function. So yeah, we're creating our memory pool and we're burning through this memory completely by doing no deallocations at all. So let's just give that a go. And it doesn't crash, but there's no real way of knowing if it's properly worked, but it doesn't look like anything's gone wrong there. We've allocated from our pool. So that is pretty much an incredibly simple Arena Allocator. Let's call it that. Let's just call it what it is. It's always nice when you call things what they are. Arena Allocator. There it is. So we've now got our little Arena Allocator. And sometimes the name pool and arena are interchangeable. You can imagine they're the same kind of things. It's a little area of stuff, but it's one area. So, and I've called it Arena. Arena. So yeah, it's just one block of memory that that you need to allocate. Let's just fix these names up. Does that still compile? Yes. Does it still run? Yes. So the only last thing we might want to do is you might want to put some debugging in here, but for now I'm just going to print out. Now I've got an allocate, a deallocate, and a reallocate. I'm just going to print out in here. It's going to print some information. You wouldn't want to do this in an actual program, but you might want to have it in some debugging mode. But let's just look at what it's doing, or what Lua is doing. So let's see if we can. So we're just going to print out the number of bytes that we allocated every time we hit that function. We don't know how many bytes we're deallocating because we haven't passed that in. So we deallocated some number of bytes there, and in the reallocate case, let's have a look at that one. So we'll say reallocated. Let's just put the new size in. reallocated. So we'll put in the size that we allocated to. So we're just going to put some printouts in there, and let's see if we can tell what's going on. Oh, there we go. So there you go. You can see that. I mean, this is a Lua program that isn't even doing anything. So this is just like new state and then close, and you can see all these allocations that we had to do, and you can see they're quite small as well. That we had to do to just make the state, and probably down here is where it's getting rid of the state. So that's a Lua program that doesn't do anything with what looks like 30 or something memory allocations. You see that big one at the start, that's probably the Lua state, and then there's a couple of other big ones. But down here, yeah, there's not a lot happening. And these would have all been coming from the OS by malloc would have been going over to the OS, and some critical section would have been locked. And that's another good point, is that this allocation scheme doesn't have any threading involved. So this is going to make the assumption that you're running this particular Lua state on a single thread. So this is again faster because there's no locking or anything involved, because we're going to make the assumption that no one else is using this state from another thread, which we can do, but the operating system can't. So we can get better performance like that. Let's see if we can. Let's pass in the size that we're deallocating, because we do know that, don't we? Allocate, deallocate. I think original size will be the size will be the original size that we were the block we were deallocating. So let's just put that in there as well, so we can actually see what's going on. We can see how many bytes it's deallocating. Function does not take one argument. Oh, yeah, pass that through to deallocate. Here, that's the size we were deallocating. So let's have a look. Oh, and there we go. So now we can see how many bytes not only how many memory allocations were happening, but how many bytes we're allocating. And and there's a deallocated 0 bytes. That's interesting. The first thing it deallocated was 0 bytes. Let's have a look at that case. Let's put a breakpoint in deallocate. We'll put a breakpoint in deallocate and we'll have a look. I think we'll hit that first time maybe. Deallocate. Oh, that's a reallocate. Oh, I'm in the wrong place. That's what's going on here, I think. Let's try that again. Oh, there you go. Original size 0. So what happened there? Original size 0 and pointer was null. So we were trying to deallocate. Well, Lua's obviously trying to do that. Lua is trying to deallocate a null pointer that has for a block that has no size, and it's trying to deallocate, and it has no new size. So that's really kind of a pointless operation there, isn't it? It's like this block never actually existed, so we can't actually deallocate that. So maybe we should just put an assert in there to say pointer not equal to null pointer. Can't, yeah, so for our purposes we're going to say can't deallocate null. We just can't do that because this doesn't make any sense to us. Yeah, we're trying to deallocate 0 bytes. So that should assert. Yeah. Line 1047, that was our assert. So we'll handle that in here. We'll say if pointer is not equal to null pointer, because we can't deallocate a null pointer, so let's just not do that. And that's fine because we don't need to do anything in this case. So let's see if that works. And there we go. So we've got everything. Well, it looks like it's deallocating correctly. Looks like it's allocating correctly. That seems all quite reasonable. So what we've done there, yeah, is we've done quite a cool thing. We've basically allowed our Lua state to allocate all of its memory from our C stack. So we've put 20k of memory on there. It's just lucky that our memory fitted as well, because if we didn't allocate enough memory, like let's allocate 1 kilobyte. There was a 1 kilobyte allocation there, so this isn't going to work. Let's see what happens. Oh, it's gone totally wrong. So it's just stopped there at that point. So you can see what happens if we don't allocate enough memory, something goes really wrong for us. So that's again something you can handle in your allocate. If your Arena Allocator runs out, you could go back to the malloc and free system. But what we probably should do in ours is in allocate, we should probably just assert down here, because if this current now is greater than the end, then, or if it's greater than equal to end, we have run out of memory. We have run out of memory. And this is the point here where you'd really want to possibly pass through to another allocator like the malloc and free, and that's where you could handle, oh, what do we do when we've burned through all that memory that we had. Let's just see if that works. Oh, did that not work? We didn't assert. Resize. Oh, it didn't manage to do anything correctly there. Allocate, deallocate, reallocate. Yeah, that should... Maybe I've got something wrong here. Maybe it's if... is it if current plus... If current plus size in bytes is greater than or equal to end, we can test that before we allocate. Let's see if that's better. Nope. We already passed our allocation on the first one. We only allocated 1 kilobyte of memory. So what's going on there? I am on the wrong line for this breakpoint. So we're trying to allocate 1552, and we passed that assertion. Current plus 1552. Oh, we have to assert. I'm doing the wrong assertion. Ridiculous. I need to assert that it's less than end. Otherwise we run out of memory. There we go. Idiots. Right, here we go. Asserted. Let me do it without the debugger attached. There we go. Assertion failed. So that's pretty good. We're not handling out of memory, but at least we're asserting that we've run out of memory. So you know what's going on there. So how much memory does this Lua state need? Let's try 5 kilobytes. Did we make it there? Looks like we made it with 5 kilobytes of memory. That wasn't a lot, was it? It's not a lot of memory, but then that is a Lua state that does nothing. So looks like we can successfully make the Lua state with just 5 kilobytes of memory. Let's try 2. This should probably fail. Yeah, there we go. So that's pretty good. That's a really, really basic memory allocator that shows that it's not that difficult to write your own really simple memory allocator. And keep in mind, we didn't have to... This Arena Allocator, we put it on the stack, but we didn't have to do that. We could have just malloced or operator new to 50 megabytes of memory on the heap here and just burned through that. And that would have mean you could have had a Lua state that could have run for ages and done so much stuff. And it would have had enough memory to work on. So this is really good. You need to keep in mind that if you do change the memory allocation scheme for Lua, that you can get possibly a lot better performance out of it and make it work in the way you want. And it's surprising to see how many memory allocations Lua's doing. Even in a program that does nothing, Like, you might not have thought that all this was happening even before you started your program. But it's one of the reasons why you can see why scripting is going to be slower than native code, because there's no way a piece of native code that does nothing would do 30 memory allocations. And this is not like ragging on Lua or anything. This is just going to be the same for any scripting language. It needs memory to work with. So the fact that Lua is giving you the ability to allocate that memory yourself allows you to work around some of the problems that you'll get with scripting languages, is that all stuff like this has to happen. So that's really good. So next time, I think I'll just we'll probably stick this Arena Allocator into its own file, and we might just use this as our standard allocator for all our Lua stuff going forward. And we might want to also maybe next time we'll also look at I'll show you how you can reclaim some of this memory that's being deallocated, and then we'll also handle this out of memory case as well. So we might as well build a fully working Arena Allocator just to show that it's not that difficult. So we'll try that next time.